So let's start our preparation from the beginning of chapter 17. And this was the first example I gave you when we were talking about KSPs. So this question gives us a KSP for mercury 1 chloride and wants to know first what are the concentrations of our two ions, our mercury and our chlorine. And I just want to break this down for you because you may not have seen this guy yet. This is the structure of this compound. And it's because the mercury is actually a diatomic metal. Pretty cool. So the first step is always to write this out as a chemical equation. So we'll start with that. mg2cl2, mercury 1 chloride. And this is solid. So this is before anything's happened. We're going to put it in solution. So we're going to get our mercury 2 plus, because there's 2 of the chlorines, and that's aqueous, plus 2 of our Cl minus, our chlorine ions, and that is also aqueous. Now let's do our little mini ice table. So we're going to start with 0 here, and we're going to gain some amount x and some amount 2x because of the coefficient of 2. Now let's go ahead and write out our Ksp expression. Now remember, unlike our equilibrium constant expressions, this does not include the solid piece. That stays out. So we're only interested in what is going to dissociate. So this will be our concentration of our mercury ion times the concentration of our chlorine ion, and that quantity squared again because the coefficient here. Remember, the 2 does not go in here. This would be something that you would determine in lab. And this is actually taking into account the molar or the stoichiometry, the coefficients involved in the breakdown of this compound. So now next step, go ahead and write it with our x's in it. X and 2x squared. And now let's simplify that. Goes to Ksp equals 4x cubed. So now we can actually solve because we have a Ksp concentration number, and that is 1.38 times 10 to the negative 18. And we're going to divide by this 4. Divide by the 4. We're going to take the this cubed root of that, and that will give us the value of x. So the value of x then, this solution here, is what the actual mercury content is, and then we can use that to find out what the chlorine ion concentration is. So I put that in my calculator, and I get that the concentration of my mercury, 2 plus, equals something. There we go, 7.01. 01 times 10 to the negative 7. Now, my chlorine ion, that's going to be 2 times x, so 2 times this value will give me my chlorine. And that will be 1.40 times 10 to the negative 6. So those are my 2 concentrations of those 2 ions in this fully saturated solution. Because remember, Ksp is the maximum amount of dissociation, or the concentration of these different ions that we can get from some given solid or salt put in a solution. Okay, so let me repeat that. Ksp is the maximum amount that we can get dissociated of salt for these ion concentrations in solution. So once we've solved for this, then we have said that this quantity here is the maximum amount of ion concentrations we can get in this solution. This is it. This is our final answer for this. So then the next step would be, we have this, we want to know what our molar solubility is. Okay, so now let's pretend that we know we are at the Ksp, we're at the maximum amount. So I'm going to take this value of x, this 1 mole of this, and dissociate all of it. I'm going to say I have precisely enough concentration that all of this will go into solution. So that means that that x that I solve for is indeed the molar solubility of this compound. So 7.014 times 10 to the negative 7. That is the molar solubility. So if we have that, then the next question that we like to ask is, what is the solubility? So molar solubility is moles per liter. Solubility is grams per liter. So this becomes just a conversion. 7.014 times 10 to the negative 7 moles of mg2cl2 per 1 liter of solution times the molar mass. And the molar mass is, or no, I wrote that, 472 grams of mg2cl2 per 1 mole. So then my moles cancel out, and I am left with my grams. Let me punch that into a calculator. So after I crunch that out, I get that 3.31 times 10 to the negative 4 grams per liter will dissociate. So what does this mean? If I have measured this much out on my analytical scale and I put it in 1 liter of solution, it will completely dissociate. And I know how many moles that is. So that is the first part in our KSP adventure. Let's see if I can get it to shut off. Come on. Work with me here. You're killing me, Seymour. There we go.